In this section, we will look to implement a machine learning-based algorithm to train a linear model to fit a set of data points. As this course does not assume any prior knowledge with deep learning, we'll begin our discussion with the notion of supervised learning, what it is and how it relates to this course. If you've taken one of my deep learning courses before, the material in this video should be very familiar to you. We will begin with a very broad definition. What is machine learning? A simplistic definition is that it's the concept of building computational algorithms that can learn over time based on experience, such that rather than explicitly programming a hard-coded set of instructions, an intelligent system is given the capacity to learn, is given the capacity to detect and predict meaningful patterns. While one can distinguish between supervised and unsupervised learning, let us consider supervised learning. In supervised learning, the learner is trained and makes use of datasets associated with labeled features which define the meaning of our training data. That way, once introduced to newly inputted data, given a new input, the learner is able to predict a corresponding output. Before discussing any more theory, let's jump into some code. We will be writing our code using Google Colab. Accessing Google Colab is very simple and intuitive. There is no setup required. It runs entirely on the cloud. To access it on your browser, search up Google Colab, and it should be the first link. Make sure you're signed into your Gmail. If you don't have a Gmail, you'll need to make one. And once you're logged in, simply create a new Python 3 notebook. And we will call this notebook Tensors Crash Course. This is quite similar to Jupyter Notebooks. We will eventually be using it for its free GPU, but notably, many packages come pre-installed for us when using Google Colab. Unfortunately, Torch isn't one of them, so in our first cell, we run the following installation. pip3 install Torch. Alright, and as it's installing, inside of our first cell, we import Torch. The ultimate goal of this project will be to create a dataset, which generally will follow a linear pattern. Then we'll declare a line, a linear model, with some random set of parameters, which chances are will incorrectly fit our dataset. However, then we make use of a simple optimization procedure known as gradient descent, which is often used in many machine learning algorithms. What this optimization algorithm will do is minimize the error function of our linear model, and it keeps doing so until the model is trained to fit our data really well. Our first step in this venture will be to declare a linear model and use it to make predictions. So we initialize two variables, w and b. And the reason for this being, we know the equation of a line can be modeled as y is equal to w times x plus b, where w is the slope, the weight, and b is the bias term, the y-intercept of our line. These are the parameters which distinguish our line, and ultimately with linear regression, provided with a bunch of data points, we first start with some linear model which most likely will not fit our data well. We then use these data points to train a linear model to have the optimal weight and bias values, that of which will provide us with the line of best fit. And then after training this model to have suitable parameters, given an input x, we can then use this linear model to make a prediction y. Alright, so back to our code, we set w is equal to torch.tensor, and we will give the weight some random value, say 3.0. And as we will be training our model, we will require the gradient of our linear function. So requires grad must equal true. All right, don't worry about why we did this for now. It will be more apparent to you later on why we need the gradient, but for now we do the same thing for the bias term. We'll just copy and paste that, call this b, delete this one, and instead of a value of 3.0, let's change this to 1.0. It really doesn't matter. And now given a linear model, y is equal to w times x plus b, provided an input x, we can make a prediction. We can determine the output y. And the purpose of this lesson is to show you how to make predictions with PyTorch, provided that you do have a model. To do so, what we're going to do is actually copy this, delete it, and on a new cell, we define the forward function, def forward. And this forward function receives the input, the independent variable, the x value, and this input is going to be passed into our linear model. Y is equal to w times x plus b. W and b being the parameters of our line, and then based on the input x, we predict the corresponding output y. A prediction is computed and returned. Returning y, let us now test our model by going inside of a new cell, and we set the input x is equal to torch dot tensor. We will choose an input of 2, and outputting the result of forward x, our model makes a prediction of 7. Instead of passing only one output, one can pass in many inputs. Suppose you wanted to make a prediction for the input 4 and for the input 7, respectively. Our forward function expects only one argument x, so we must wrap this up in an extra set of brackets such that it receives both 4 and 7 as separate inputs, and the computation will occur as follows. Making a prediction for the input 4 to be 13 and for the input 7 to be 22. That is all for making predictions. In the next video, we will look into a more standardized way of creating a linear model. I will see you there. Welcome back to another lesson. In the last one, you learned to make predictions using a linear model. In this video, we will look at a more standardized way of initializing a linear class. We will discuss the theory as we implement it into code. So on a new Python notebook, first you must import the relevant torch library, and from torch.nn, we will import the linear class from the nn module. You will first write the following line of code on a new cell. Torch.manual. We seem to have a problem, being that I have to rerun this cell. And so I'm just going to fast forward this video until I do. See you in a bit. All right, and we're back. We will start by finishing up this line of code, torch.manual_seed1. What this does is it sets a seed for generating random numbers. The reason we're doing this is when constructing our model with the linear class, it will be given random values for the linear class, which makes sense since, recall, we start with a random value for the weight and bias, and then we train our model through a gradient descent algorithm to obtain the optimal parameters to fit our data. We'll talk about training shortly, but for clarity and to see progress in training our network, we want to ensure that the random values assigned to our weight and bias values are consistent. Hence why we set a seed. The seed can be anything that you want it to be, so long as you don't change it. If you wish to obtain the same results that I get, then feel free to use the same seed. All right, let us now construct our linear model with model is equal to linear, and it will accept in features is equal to 1, out features is equal to 1. What this means is that for every prediction that we make using our linear model, for every output, there is a single input. By creating this object over here, we've created a linear model. And we can determine the parameters of this line by printing print model.bias as well as model.weight. We get our weight and we get our bias value. This would result in the equation y is equal to 0.5153x minus 0.4414. Perfect. Now, provided this model, we can now make a prediction based on an input x, which we will set equal to torch.tensor, and we will pass in an input of 2.0, noting that this is a float value, and we will call upon our model, and pass in x as an input. This should return a prediction, which we can print out. Print model x. It outputs a prediction of 0.5891. One can make several predictions by passing in several inputs. We can pass in an input equaling 3.3, and noting that our linear model only takes in a single argument, we must enclose this in a bracket. So what's going to happen is, for each input, we will get one output, one prediction. And printing this out, the prediction for 2.0 is the same thing as earlier, and we also get a prediction for 3.3 to be 1.2590. This lesson was to get you familiar with the linear model class, which provides a more concise, easier, and more standardized way of constructing a linear model. We will be using this class all throughout this course. In the next video, we will explore custom modules, a robust and efficient way of building neural networks with PyTorch, and for the purposes of this section, we will use it to further configure our linear model. I will see you there. Hello everyone, in this tutorial we will explore custom modules, a robust and intuitive way of building neural networks in PyTorch. We will build more complex neural models in the next section and thereafter, but for now we'll simply use it to build our simple linear model just to learn how to do it. Now that you're more familiar with the basics, the method in which we're currently going to implement model construction grants you more freedom and is much cleaner and more intuitive in its implementation. So on a new collab notebook, I've already went ahead and imported Torch, and inside of a new cell, we start by creating a new class, which I will call LR as in linear regression. And I know that we haven't covered classes in the Python crash course, so if you're unfamiliar with them, we can go through them now very quickly as we go along. But essentially, we will use this class as a template, as a blueprint for our model's construction. Generally, it is a template for creating new objects, new instances of our LR class. Our class will be immediately followed by the init method, which can be written as def init. Ensure that you use the double underscores before and after the method. If you come from another programming language, for example, ES6 JavaScript, this would be known as a constructor. And so we use this initializer, we use this constructor to construct, to initialize new instances of this class. The first argument for our initializer is usually self, where self simply represents the instance of the class, the object that's yet to be initialized, and then after self, we can add additional arguments. Our choice for these arguments is dictated on the basis that we are using this class to initialize a new linear model instance. If you look back at the previous code, initializing a linear model requires that we have an input size as well as an output size. In this case, 1 and 1 for both, since each input will produce one output. But we will be more general inside of our constructor. That is, the arguments passed in will be input size and output size. Whatever input size and output size is passed in as we create our instance. And perfect. That is all. Now to create a linear model, to access our linear class, we first needed to import torch.nn. Let's do that again. We will import torch.nn, but this time let us do it as the alias nn. We will use inheritance such that this subclass will leverage code from our base class nn.module. Module itself will typically act as a base class for all neural network modules. In this case, the linear regression model class will be a subclass of nn.module. thereby inherit methods and variables from this parent class. And when dealing with class inheritance, one should be mindful of calling super.init, which simply allows for more freedom in the use of multiple inheritance from parent classes. Alright, now this is just boilerplate code that you always need to write to create your custom class. And now, having performed all the necessary steps to inherit from our parent class, we will declare self.linear, which represents the instance of the class, the object that we intend to initialize, and it will be set to nn.linear, as we've done before, accepting both the input and output size that's being passed in. Input size and output size. Great, we finally finished our initializer, which we can now use to initialize a new linear model. We can do this by setting. We seem to have made an error, and that is because I should run this before running nn.module. Okay, back to it. We will initialize a new linear model, an instance of this class. Model is equal to LR, and we can pass in 2 arguments into the initializer as clearly shown. As before, we pass in an input size of 1 and an output size of 1 as well. And there is our linear model. You can now seamlessly create more linear regression models to your heart's content. We will stick with 1 and print out the random weight and bias values that were assigned to it from nn.linear. We do this by printing model.parameters, and we will print it as a list in order to better see our results. And before making any conclusions, as done before, we will seed our random number generator to see consistent results with torch.manual seed, and it will contain the same seed as earlier, 1. All right. And our weight term equates 0.5153, and the bias term negative 0.4414, as before. And now recall, to make predictions, we make use of the forward method. And conveniently, we can define the forward method inside of our class such that the method can be accessed for every instance of the class. So we write def forward, once again, the first argument being self, and arguments thereafter being the ones you need to actually pass in. In this case, we pass in the input x. All right, and now forgot my colon. And now the prediction pred will equal the prediction that comes out of x being passed into our linear model, self.linear. Let's not forget our brackets. And we will return the prediction, return pred. Running this cell and back here. We can now use this method for any instance of our class. In this case, we will use it for our model. So we write model.forward, and into it we pass in a tensor as we have always done. So we write x is equal to torch.tensor 1.0. Ensure that this is a float, and into our forward function we put the x and print the result. Print model.forward x, like so. And it outputs the appropriate prediction. We can try this for 2 values of x, 1.0, 2.0, wrap them up in a single bracket. And yet it's consistent, as it now makes 2 predictions based on 2 independent variables, such that for every 1 input there is 1 output. Very well, you should now have become very comfortable in making predictions using the linear class in an object-oriented programming approach. Going forward, this is how we will approach model initialization in this course. The next step before we conclude the linear regression section is to actually train our model to develop new weight and bias values based on previously labeled data, rather than just working with the random parameters. We will do that going forward. Welcome back to another lesson. Previously, we looked at various ways of making predictions with a linear model using PyTorch, and worked our way up to a more standard way, that of which will be implemented going forward. Before we start discussing the machine learning concepts involved in training our model, before we even train our model to fit a dataset, we must actually create this dataset first and plot it. As such, we will keep this video short. If you wish to skip this preliminary step and simply move on to the next video where we train our model, I've included the source code in a subsequent article, as well as on GitHub. Otherwise, if you wish to follow along, feel free to use this earlier notebook as a starter project, as we will be simply building over it. Firstly, for visualization purposes, we begin by importing matplotlib.pyplot as plt, as we have always done before, and instead of pressing Shift and Enter to run the cell, press Alt and Enter to create a new cell right below, as it is in this cell that we will be creating our dataset. Ultimately, this is the dataset that we will try and fit a linear model into. Our dataset is plotted on a two-dimensional coordinate system, such that each data point is characterized by an x and a y coordinate. As such, we will be specifying the x values for our data points, which we will set equal to torch.randn, and what this does is it returns a tensor filled with random numbers that are normally distributed. This function accepts a sequence of integers which define the shape of our tensor. We want our tensor to have 100 rows and 1 column, such that there will be 100 points, and each point has a single value within the normal distribution. If we print this value, print x, it outputs a tensor filled with numbers that are normally spaced out. However, the numbers are relatively small since they are centered around 0 with a small variance. So what we can do is multiply all the numbers in the scalar by a value of 10 times 10 to set up a larger range. As we are dealing with a two-dimensional coordinate system, each data point will have both an x value and a y value, which we will set equal to the output y. For now, will simply be a function of x. To further modify the y value, let us simply plot our current set of data points with plt.plot x. Recall this must be converted to a NumPy array, and the y value as well, y.numpy. And we want each data point to show up as a circle. So what we can do is just place the letter O as our third argument, O not 0. Outputting this should result in a straight line of data points. This was to be expected, such that all data points are normally distributed within the x. Alright. Now fitting a linear model into a straight line of data points would be relatively easy. We will challenge our model by adding a bit of noise to our output. To each y value of the point, we want to shift it upwards or downwards, such that the noise is also normally distributed across the entire range. So instead of just setting the output equal to the input x, let us add this normal distribution of noise to all 100 points by adding torch.randn 100 to 1. And recall that randn will center around the 0 with a relatively small standard deviation. We want data points to be relatively spaced out, so we want the noise to be reasonably significant. As such, we'll multiply the noise ratio by 3. 3 times torch.randn, and this should create our noisy dataset. Alright, now for aesthetic purposes, or actually for clarity, let us assign the y-axis a label, plt.ylabel, y. The x-axis as well, plt.xlabel. Alright, and we are good to go. We have our noisy data, and now that we've created our data set, it is time to train a model to fit this data set. Seeing that we've already done the code for creating a model, we will reuse it. This linear model that we currently have, it has random weight and bias values. Random parameters assigned to it from the linear model. One can only assume that this model does not fit our data well. All right, well, let's see for ourselves. What we'll do is we'll create a new cell. You know what we'll actually do is just delete what's inside of this cell, delete these cells as well. You can do so by pressing Control M and D, and over here, inside the cell, we will first obtain the model parameters by unpacking model.parameters into a list of two elements, W and B. And before proceeding any further, it seems that none of our cells are run, and I'll just go ahead and add a print model in here to see an output. But aside from that, let's rerun all of our cells to ensure that everything goes by smoothly as we go along. All right, back to it. We were unpacking model.parameters into a list of two elements. Don't forget your brackets. And now printing W and B. And we see that the weight is a two-dimensional tensor with one row and one column. So we can access this weight 1 is equal to the weight at row index 0 and column index 0. And same thing for the bias term, except it is only a single dimension within the 0th index of our tensor, B0. All right, and printing both values, print W1 and B1. We obtain them, let's remove that. We obtain them as a tensor type. We can actually add .item to both terms, and what that's going to do is give us a Python number from both tensor values. Outputting this, we get our parameters. All right, and let's make this into a function for cleanliness. What we can do is write def get params, and this will return the two values as a tuple. It will return w00.item as well as b0.item, removing the following. Now on the next cell, we will plot our linear model alongside the data points. So we will call a function def plot fit. The argument it will accept is a title, where our plt.title will equal the title that was just passed in. And now since matplotlib is most compatible with NumPy, let us first actually, on top, import NumPy as NP. We know the equation of a line is also y is equal to wx plus b. We have w, we have b, as they were initialized once we created our model. So what we can do is determine numerical expressions for x1 and for y1. So first what we do is we set w1 and b1 equal to the return value of get params. Our x-axis seems to go from -30 to 30. So what we can do is simply set x1 is equal to numpy.array -30 to 30. Make sure this is an array, not a tensor, to ensure compatibility with pyplot. And now from these two x1 points, going from one extremity till the end, we can get two y points. We can compute y1 is equal to w1 times x1 plus b1. Ultimately, this will return two y1 points, one at -30 and another one at 30, which will be connected by a line, hence plotting our linear model. All right, let's plot it. plt.plot x1, y1, and given that our data set is blue, let's plot it as a red line by specifying the string r. All right, and that's it. Now we also want to plot our scattered data points, and we do this with plt.scatter. We will plot x and y. And finally, showing our plot with plt.show, and on a new cell, we simply call plot fit, with the title being initial model. All right, plotting our model alongside the data points, we can clearly see that this is not the line that best fits our data. We will need to use gradient descent to update its parameters. We will start doing that going forward. Hey, welcome back. Hope you're doing well. Previously, we created a set of data points and initialized a linear model. We will now move on to the next step, which is, provided a set of data points, it is our goal to find the parameters of a line that will fit this data well. As we've seen before, the linear function will initially assign random weight and bias parameters to our line. Suppose it returns a line with the following parameters. Clearly, this line does not represent our data well. We need some kind of optimization algorithm that will adjust these parameters based on the total error, until we end up with a line containing suitable parameters. How do we determine these parameters? For simplicity and to get a brief understanding, let's limit our discussion to a single data point. Whatever line that we choose, the error is determined by subtracting the prediction at that point from the actual y value. The closer the prediction is to the y value, the smaller the error. The prediction, as you should already know, can be rewritten as wx1 plus b. However, since we're dealing with a single dot, an infinite amount of lines can be drawn through it. So we will remove the bias, removing that extra degree of freedom for now, and we can cancel it out by ensuring the bias term is fixed at 0. Alright, now whatever line that we're dealing with, the optimal line will have a weight that will reduce this error as close to 0 as possible. Say we're dealing with the point -3 and 3. The loss function would translate to 3 minus w times minus 3, all of that squared. Now what we're going to do is make a table and try out different values for w and see which one gives us the smallest error. A weight of -2 results in the following, which has a total error of 9. A weight of -1.5 gives us an error of 2.25. Notice how the error is analogous to the spacing between the predicted value and the actual value. The smaller the spacing, the smaller the error. A weight of 1.5 gives an error of 56.25. 2 gives an error of 81. However, if we use a line with a slope of -1, a weight of -1, clearly this perfectly fits this point. If we calculate the error between the predicted value of our linear model and the actual value, the error is 0, which makes sense as the prediction lines up well with the actual labeled value. The different errors, they vary based on which weight parameter to use for our line so that it fits our points. I've plotted different error values for different weights in Matplotlib for visualization purposes. Clearly, the absolute minimum in this case corresponds to a weight of -1. Now that we know how to evaluate the error corresponding to our linear equations, the question remains, how do we train a model to know that this weight right here, that is the weight parameter that will yield the lowest error? Let's talk about that in the next lesson. Welcome back, hope you're doing well. Previously we looked at and evaluated the loss function of various linear models with respect to different weights. We saw that given previously labeled data, there exists weight parameters for a line that will yield the smallest error. The question remains, how do we train a model to determine the weight parameters which will minimize our error function the most? Well, this is where we introduce gradient descent. The way this works is that first your linear model will begin with random initial parameters. Recall when we initialized a model with the linear function, it indeed gave us random initial parameters. Let's ignore the bias value for now. And based on the error associated with this initial parameter, w, we want to move in the direction that gives us the smallest error. The trick is, if I take the gradient of our error function, the derivative, the slope of the tangent at the current value that I'm at, this derivative will take us in the direction of the highest error. So what we do is we move in the negative of the gradient. This will take us in the direction of the lowest error. So we take the current weight and we subtract the derivative of that function at that same point. This will take us in the direction of the least error. We are descending with the gradient. However, to ensure optimal results, one should descend in really small steps. As such, we will multiply the gradient by a very small number, known as the learning rate. The value of the learning rate is empirical, although a good standard starting value tends to be 1 over 10, or 1 over 100. The learning rate needs to be sufficiently small since as the line is adjusting itself, you never want it to move too drastically in one direction, as that can cause for unwanted divergent behavior. Throughout the course, you will learn to adjust the learning rate based on empirical results, and we will code a gradient descent algorithm in the next few videos, but to just end this lesson, and to follow through with our gradient descent example, let us refer to a demonstration on Excel in order to simply visualize the effect of gradient descent. Alright, as you can see on top, we have the coordinates of the point themselves, x and y, and below I've set up 2 columns, the weight and the error. The initial weight is clearly negative 1.5, and I've set up the spreadsheet such that the second weight is equal to the value of the first weight minus the derivative of its error function at that weight times a learning rate of 0.01 to give us the new weight. Thus, at each step, we are moving in the negative of the gradient, and if we do it for one step, notice that the error gets smaller. And if we keep doing it for subsequent cells, notice how the weight eventually converges to -1, such that the error at that value approaches 0. This is consistent with the graph that we observed earlier, as a weight of -1 would indeed yield the smallest error for the point -3 and 3, as we saw in the last video. Alright, so clearly gradient descent, descending in the negative of the gradient, is a very effective approach in training our model. Don't worry too much about this Excel sheet. This was purely for visualization purposes. If you want, I can include it as a resource for this lecture if you wish to play around with it. In the next few videos, we will work our way up to implementing gradient descent into our code. But before doing so, let us discuss the mean squared error. We'll do that in the next section. Welcome back to another lesson. Let us conclude the theory part of this section by discussing the mean squared error. The mean squared error is calculated in much the same way as the general loss equation from earlier, except now we will consider the bias value as well, since that is also a parameter that needs to be updated during the training process. The mean squared error is best explained with an illustration. Suppose we had a bunch of values, and we start by drawing some regression line parameterized by a random set of weight and bias values. As before, the errors correspond to how far the actual value is from the predicted value, the vertical distance between them. The error for each point by comparing the predicted values made by our linear model with the actual values using the following formula. Each point is associated with an error, which means we would need to take the summation of the error for each point. Do note that the prediction can be rewritten as wx plus b. As we are calculating the mean squared error, we then take the average by dividing by the number of data points. And I mentioned before, the gradient of the error function should take us in the direction of the greatest increase in error, so naturally by moving towards the negative of the gradient of our cost function, we move in the direction of greatest descent, in the direction of the smallest error. We will use this gradient as a compass to always take us downhill. For simplicity, in the last video we ignored the presence of a bias, but the error is defined by two parameters, both m and b. We're not going to go through the math since PyTorch does all of it for us out of the box, but really, it's the exact same concept as earlier, where we differentiate our error function, but this time, since our error function is defined by two parameters m and b, we compute a partial derivative for each, and just like before we start with any m and b value pair, we use the gradient descent algorithm to update m and b in the direction of the least error. And we update them based on the two partial derivatives up above, such that for every single iteration, the new weight is equal to the old weight minus its gradient times the learning rate, and the new bias value is equal to the old bias value minus its corresponding gradient value times the learning rate. When implementing gradient descent into our code, we're not going to have to worry too much about the math, as PyTorch does all of it for us out of the box. It's just nice to know what's going on under the hood when you write your code. The main idea being, we start with some random model with a random set of weight and bias value parameters. This random model will tend to have a large error function, a large cost function, and we then use gradient descent to update the weights of our model in the direction of the least error, minimizing that error to return an optimized model. That is all, guys. Let's put all of this into code. I will see you then. Welcome to another lesson. Let's jump right into implementing gradient descent. The first step is to specify the loss function that we intend to minimize. Given what I've shown you, you might think to specify it according to the following equation. However, PyTorch allows us an easy way to specify the loss function. We can access the built-in loss function from nn.mseLoss. Very easy. The mean squared loss, and store this in a value called criterion, or a variable I should say. Not too hard. All right, the next step is to specify the optimizer that we will use to update our parameters. The optimizer will use a gradient descent algorithm, notably stochastic gradient descent, an optimization algorithm that we can access from torch.optim.sgd, as in stochastic gradient descent. You may be wondering what stochastic gradient descent is. The gradient descent algorithm I showed you before is known as batch gradient descent, which computes the gradient using the entire dataset by updating the weights based on the sum of the accumulated errors. This can be very bad, since imagine you were dealing with 1,000,000 points. Running the same batch gradient descent process as earlier, where you'd have to evaluate the accumulated error for every single data point, for every iteration, that would prove very costly. Whereas with stochastic gradient descent, it minimizes the total loss one sample at a time, and typically reaches convergence much faster as it will more frequently update the weights of our model within the same sample size. Although the expression for SGD is different, the general concept remains the same, such that we're still updating the weights towards the negative of the gradient. It's just that now with stochastic gradient descent, it's mostly computationally faster. Alright, back to our code. In the first argument, we specify the model parameters that should be optimized. In this case, model.parameters. And for the second argument, we must specify the learning rate, LR. A reasonable initial learning rate is 0.01. And recall that learning rate simply corresponds to the tiny steps that we would take to reduce the error in every iteration. These tiny steps need to be sufficiently small, since as the line is adjusting itself, you never want it to move drastically in one direction. as that can cause for unwanted divergent behavior. In the near future, we will look to implement adaptive learning rates and look to see how one can further fine-tune these hyperparameters, but for now, 0.01 should be enough to observe a significant, yet quick drop in the loss function. Alright, so now that we've specified the configurations for our training process, it is now time to train our model. We will train our model for a specified number of epochs. An epoch is simply whenever we perform a single pass through the entire dataset. As we iterate through this dataset, we calculate the error function and backpropagate the gradient of this error function to update the weights, as you saw earlier. Okay, so how many epochs should our line go through? Let's recall the concept of gradient descent, which updates the weights and biases of our network in the direction that decreases the error function the most. It's an iterative process, which is why we need to pass the full dataset through our model multiple times to ensure an optimized result. In other words, we need more than one epoch. If you simply specify one epoch, that leads to the underfitting of a curve, which doesn't capture the underlying trend of data. As the number of epochs increase, the more times it's able to update the weights of the neural network, minimizing the error, and thus producing optimal results. At the same time, you don't want to pass in too many epochs, since that can lead to overfitting, generally, which is a modeling error that occurs when a function is too closely fit to a limited set of data points. For this specific scenario, overfitting shouldn't pose too much of an issue. We'll see examples of it later on. We will just stick to 100 epochs, which would provide more than enough training iterations for our model. Alright, and now for every epoch iteration, for I in the range of epochs, given that for every epoch we want to minimize the error of our model such that the error is simply a comparison between the predictions made by the model and the actual values, let us first grab the predictions with ypred is equal to model.forward x. So for each x value, we make a prediction using the forward method, all of which is stored inside of ypred, and then we compute the loss. We set loss is equal to the criterion, which we set equal to the mean squared error. And we will calculate the mean squared error for both the predicted values as well as the actual values y. Let's make sure I called it y. And indeed I did. And now for every epoch that we iterate through, we will print the epoch. We will print the epoch I. Let me make these into double quotes. Ran it by mistake. Alright, so we print the epoch I that's currently being iterated through, as well as the loss associated with that epoch. Loss.item. Forgot my comma. Alright, simple enough. And now in order to visualize the decrease in loss at every single epoch, what you want to do is before the for loop, we're going to set a list, losses is equal to an empty list, and for every loss that we compute, we will append it into our losses list. We do this with losses.append loss. All right. Now having computed the loss, at every epoch we must minimize that loss. Recall in gradient descent, we must take the gradient of the loss function, the derivative. And recall to compute the derivative, we use the dot backward method. This was in the intro to tensors section. We call loss dot backward. And having computed the gradient, we update our model parameters with optimizer dot step, using the optimizer that we initialized earlier. All optimizers implement the step method that's used to update the parameters of our model and can be called once the gradients are computed with the dot backward function. as was just done. Alright, we're almost done implementing the training process of our model. Before the optimization step, we must set the gradient to 0, since gradients accumulate following the loss.backward call. And we do this with optimizer.0grad. Rest assured that every model that we train in this course will follow a very similar process, where we make predictions using our model, compare the predictions made by the model to the actual outputs, and based on that determine the loss, the mean squared error, and then we use an optimization algorithm, in our case stochastic gradient descent, to update the weights of our model in the direction of the least error, thereby minimizing the error function of our model as we attempt to minimize the loss iteratively to obtain a model with optimal parameters, the model that best fits our data. Alright, perfect. And by running this cell, we can now train our model. Alright, and notice that as the epochs progress, the loss gets significantly smaller, eventually converging at a minimum value of what seems to be 7.46. Although it's not 0, for our purposes this is really good. You have officially trained a model using gradient descent to fit a set of data points. To better visualize the process, let us now plot the loss on a graph. On a new cell, we run plt.plot. The x-axis will be the number of epochs, range epochs, and the y-axis the losses. Also, before I forget, just a fair warning, if you get really weird results for this training process, just simply make sure to restart the runtime or reset runtime, whichever one, then rerun your training process. It should work after that. Anyway, back to what we were doing. Simply plotting the losses on matplotlib, and we will give the y-axis a label, plt.ylabel. I will name the y-axis loss, plt.x label. We will name the x-axis epoch. Alright, now running this cell, this further clarifies that 100 epochs was indeed an appropriate amount of iterations to allow the model to eventually converge to a minimum loss value, as it seems to be dampening out right over here at around 7.4. Allowing our model to effectively train to fit our training data. To visualize how well the model fits our data sets, we can now plot our new linear model by simply calling plot fit train model. Plotting this data. Alright, we see our training data, and we see our linear model, which has been trained to fit our training data. And it seems like it fits it pretty well. Congratulations, you've just successfully trained a linear model to fit training data using gradient descent. If this is your first time applying a machine learning algorithm, then feel free to pat yourself on the back, as this accomplishment is a pretty big feat. In the next section, we will step it up a notch and try to build a classification algorithm. I'll see you in there. Great job on making it past the linear regression section. You've managed to train a linear model to fit a set of data points, which is pretty awesome. We're going to be training highly complex neural networks in this course, some of which will be in charge of performing highly sophisticated tasks. For now, learning how to train a model to simply fit a linear dataset is a great step in the right direction. The next step is to now use a linear model to learn how to classify between two discrete classes of data points. We do that in the next section.